Um, let's start from where we left off yesterday. So we are looking at expressions. Okay. So can someone confirm that you can see the screen and hear my voice?
Yes, sir.
Okay, wonderful. Okay, so we were looking at expressions in OCaml, and in particular, we are looking at how expressions have syntax and semantics, um, and how the semantics itself is of two kinds. One is the static semantics, which is the type of the expression essentially, which is done at compile time, and the second one is the dynamic semantics, what the expression evaluates to when you run the program, right? And in OCaml, there is a strong distinction between static and dynamic. In JavaScript, there is no static semantics. You start executing the program, whatever you write, as long as it is syntactically valid JavaScript, you start running the program. But in OCaml and other strongly typed languages, this is not just specific to OCaml. You can also think about Java as an example of this. If your program does not type check, then the compiler wouldn't let you actually run the program, right? You might also ask yourself at this point, okay, why is Java being cited as an example and not C? Of course, C also has this static and dynamic check, right? So you write some C program. If you have wrong type of argument sent over, C will complain. But C is sort of relaxed, quite relaxed, right? If you have a string and you can always cast it to some integer, right? And C will say, okay, if that's what you want, I will just allow that to happen. This leads to memory errors like crashes, segfalls, whatnot. If you've written any sort of linked list programming, I'm sure you would have faced this problem where when you run the program, C crashes, right? Of course, languages like Python, JavaScript don't crash with a memory error, but they throw exceptions at runtime. The advantage of the static versus dynamic distinction, which is very strongly done in OCaml and other functional programming languages like Haskell, and also languages like Java, Scala, and say Rust even. So there, the idea is that you want to catch many of the errors that you could potentially catch during compile time, and only let few of the errors to be done at runtime, right? And this is not, you cannot, again, I'm sort of pontificating here, but sort of bear with me. So the idea is that the distinction where you draw the line between static and dynamic is quite a spectrum. Okay, so for example, in JavaScript and Python, there is no static, but C does some of the things statically, but a lot of the things are dynamic. In OCaml, you sort of take more things to be done statically, catch static errors, and fewer things to be dynamic. So it's like a complete spectrum. So you cannot sort of say one language is completely statically typed and another one is completely dynamically typed. You can sort of put them in boxes, but this distinction of where you catch errors is quite flexible, and different languages do it at different times. We will come back to this idea over and over again. Okay, so don't worry if this if this isn't quite clear right now. But here is an example that we saw yesterday, right? So in OCaml, one of this is a static error, the other one is a dynamic error. The first one, we are saying whether 23, the integer, is equal to 45, the floating point number. Here, OCaml will just not let you run this program, right? So it will just complain saying, I am expecting an integer and you're giving me a floating point number. So this is a static error. And this is a dynamic check that fails. It's not an error. Here we are saying whether 23 is equal to 45. And both sides are integers. So OCaml is going to say, okay, this is fine. But when they are not equal, right? It evaluates the expression, and it evaluates it all the way to a value. The expression has type bool. The value also has type bool. The value is a false value. Okay, so moving on. So we have seen simple expressions. Now let's look at if expressions here. So it's very simple, but the key takeaways here is in C and Java, if is a statement, right? Here, if is an expression. What do I mean by that? Just go back to the definition. An expression has some syntax, right? And it also has static and dynamic semantics. The idea is that you will take an expression, it will have some type, right? That's the static semantics. And we can evaluate that expression down to a value. It's not like a structured block of code where you sort of do multiple operations together, right? So we have a different way of looking at ifs here. So the static semantic, so the expression itself, you write it as if some expression E1, then expression E2, else expression E3. The whole thing is also an expression, right? So each one is an expression, the whole thing is also an expression. Static semantics places some rules on what is a valid if expression. The checks are this. So static semantics looks at E1 and says whether E1 has type Boolean, right? E1 has to evaluate to a type Boolean. And then the next check it does is it checks the type of E2, right? And the type of E3. If both of them evaluate to some type T2, we don't care what this type is. If both of them evaluate to the type T2, then the whole expression has type T2, right? So it's the important bit is this, right? So because we are going to assign a single type to the entire if expression, if say the true branch returns an integer, it is expected that the false branch also return an integer, right? And only then can you say this whole if expression evaluates to some integer. And the dynamic semantics is obvious here, right? So if E1 evaluates to true, then you do E2, else you do E3. Okay. So this should be dynamic semantics should be fairly simple. So here is an example, right? So I have if 32 equals 31, then hello else world. Of course, this is false. So you're going to get world here, right? And the second example that I have is if true, then 13 else 13.4. Let's apply a static semantics rule, right? Oh, this is a Boolean. That's fine. True is a Boolean. It looks at the type of the true branch. That's an integer, right? 13 is an integer. And the else is a floating point number. So our rule here says that both E2 and E3 have to be the same type, right? Here they are not the same type. So 13 is an integer, 13.4 is a floating point number. So OCaml says, I cannot give this expression a type. If it is true, then you will get an integer. If it is false, then you'll get a floating point as a expression type. This is not something that OCaml allows you to do. So if you run this expression, you will get an error. It says um, the type that was expected here, this expression has type float, but an expression was expected of type integer, right? It looked at the true branch and it said, okay, if this is a true branch, I'm going to expect the same type for the false branch. If it is not, because it is obviously a floating point number, so OCaml is complaining. And of course, if you change it to an integer, this would work, right? So this is quite different from what you might have seen in, say, C or Java, where if is a statement. So this is sort of how OCaml encodes if expressions. So we can sort of encode this more formally. right? We will look at this formal encoding over and over again. So in this course, we are going to look at precise notion of defining the meaning of pieces of programs, right? Expressions and statements and so on. So the way we do that is through what is known as inference rules, right? An inference rule is just a easy way of writing down what you want to convey, which is it has this long bar, right? And above the bar, there could be multiple premises. So you can say if premise 1 holds and premise 2 holds and premise 3 holds up to premise n, then you can conclude that the conclusion holds, right? So this is the standard way of writing semantics. These are known as inference rules. We will look at more inference rules as we go on. So we can define the static semantics of if expression using an inference rule. So we are all we are doing is we are taking the English language statement here, right, and we are sort of writing it down in a more succinct fashion. So what we are doing is we are saying if E1 has type bool and E2 has type T, E3 has some type T, then this whole expression if E1 then E2 else E3 has type T, right? This is of course omitting a few details, but that's not important. So you can sort of read this. You can sort of read this inference rule exactly as you would read this English language statement. Okay. Okay. So that's sort of a more formal definition of the static semantics of if. We can also use the same technique to describe the dynamic semantics of if. So what is the dynamic semantics? It's very simple, right? If E1 evaluates to true, then we are going to do E2. Otherwise, we are going to do E3. So the rule here, we have two rules here. The first thing to notice is we have two rules, one for true and one for false, right? The true rule says that if E1 evaluates to true, right, then if E2 evaluates to V, then the whole expression evaluates to V, right? This is very natural. This is what we are sort of the intuitive semantics is that, but we are also making it more concrete. And similarly for the false case, right? If you say, oh, if E1 evaluates to false, then you don't care about E2 at all. We are not going to evaluate it. If E3 evaluates to V, then this whole expression also evaluates to V. So you sort of read this arrow as evaluating to. Okay, so again, I'm sort of throwing in certain ideas here, but we'll come back to inference rules and so on a little bit more. So the key takeaway in this slide is um, the inference rules and the split between static and dynamic semantics gives us a vocabulary to talk precisely about the meaning of certain expressions in a language, right? You might not have dealt with this level of precision in other languages. We sort of look at examples and then say, oh, this is how it works. But here in languages like OCaml and even other languages to some extent, we can sort of define precisely what the meaning of a particular expression or a complete program is, right? And this is quite useful because you can completely understand what goes on, not in terms of just examples, right? Oh, these examples work, but there is also this corner case. No, there is no corner case, right? This is precisely how the if expression works, right? So that's the benefit of reasoning formally about these things, so that you get a deeper understanding of how expressions work. Okay, so that was if expression, and OCaml also has the ability to define let expressions. These are sort of, you can sort of think about this is a new way to define variables. Okay, so a let expression has these parts, right? You typically write let some variable x equals some expression e1 in expression e2. So the way you sort of look at the components is x is the identifier, right? And e1 is the binding expression, and e2 is the body of the expression. and the whole thing itself is an expression. So what we are saying is the intuitive understanding is evaluate U1, right? Just take U1, which could be a complex expression, evaluate U1, store the result in X, right? And E2 can refer to X. And wherever you see X in E2, just substitute the value of X there, right? So this is the intuitive meaning. Here is even, it gets easier if you look at examples. So here is a simple let expression, and all it's doing is saying let X equals 5. I'm just going to say X is 5 in X plus 5. And it says that wherever you find X here, you substitute the value of evaluating the expression E1, which is just 5. A value is an expression. So you take 5, you substitute here, and this whole expression has the value 5 plus 5. So if you evaluate it, you get 10, right? Let is also an expression. So the static semantics is that the whole thing evaluates to an integer, and the dynamic semantics, the actual evaluation gives us the value 10, right? So yeah, this should be, you'll sort of use this very extensively. You'll start using this extensively, but the essence of this is very simple. So all you have is a binder, right? A variable, some expression on the right hand side of equality, right? Which you evaluate. You take that value, you say X is now that value in the other expression which can refer to X, right? So all that is happening is that intuitive understanding. Of course, you can sort of keep extending this. So because we have written the let expression in this way, where we have E2 is also an expression, and this whole thing is also an expression, right? So E2 could also involve a let, and you can keep doing this recursively. So let X equals E1 in let Y equals E2 in let Z equals E3, and so on until in something else. So this is precisely what is happening here. Just look at the intuitive meaning, right? We are saying let X equals 5. So let's say X is 5. Let Y equals 10. Let's say Y is 10. And this whole expression is X plus Y. So all we are saying is take 5, take 10, and then add them together here. We are just giving names for the result of evaluating these expressions. These are just plain values here. So you can sort of see what it will get, right? Again, the point I'm stressing here is it's not a special kind of construct, right? This is just applying the same rule again. So we have the whole thing as an expression. It has a static semantics integer and a dynamic semantics is 50. So one thing to note is X is not a variable here, right? So in the sense of what the term variable means. When I say variable, right? Variable is something that varies. But here, these are sort of, you sort of look at these as just constant values. So what do I mean by that? So I can the intuitive meaning is that these variables cannot be changed, right? But here is a strange example. Let's just keep that in the back of the mind. Here is a strange example. I say let X equals 5 in let X equals 10 in X. So if you evaluate this, you get a warning. Let's ignore the warning for the moment, right? And it says that the expression evaluates to 10. So the idea here is that we have one variable, sorry, we have one binder here, which binds X equals 5 in this expression, this whole expression here. And what that expression does is it again binds X. It says X is now 10. I don't care what the previous X was, X is just now 10. This is not changing the variable value, it's just defining a new X, right? It's just saying, oh, here is a new X now. in this body expression where x is now going to be 10. So this particular expression is not even going to be used, right? So these two are two different x's, and that is why the compiler is complaining, saying, "Oh, you are using the second x. This x is being used here, right? Which is the reason why we get the result 10. But the original x, which is x equals 5, is not being used." And the compiler is handily pointing out that, "Oh, here is a warning. You are not using this x." Right? Um, so the main idea that I want you to take away is we are not changing the value of x. We are just defining a new x, right? So we are just naming a new thing, and the name happens to clash with the previous one. We just um, go with the second one, and this nicely sort of gives you this idea of scopes and shadowing. So OCaml is a lexically scoped language. So wherever you see expressions, we take the scope to be just the scope where um, as how the program is defined, right? Program syntax is defined. So when OCaml looks at x equals 5 and let x equals 10 in x, it is really sort of parsing this example as let x equals 5 in some expression. That expression happens to be let x equals 10 in x. So it just happens so that the body expression, this expression happens to use the same variable name. So the previous one does not get used. So the important takeaway is x is not mutated here, right? We are not changing x. This is not like we declare a int x equals 5 and then we set x equals 10. We are not doing that. We are actually doing int x equals 5 and then we are declaring again int x equals 10. So there are actually two different x's in two different scopes, right? What is happening is the inner x, this inner x is shadowing the outer x. You will not see when you define a binder with the same name as the previous one, it just shadows the previous one. It is sort of saying wherever you refer to x in this body, it is going to refer to this x and you cannot refer to the outer x. Right? So that's the meaning of what is happening here. So what do I mean by shadowing? What is happening? So the notion of shadowing is really what it means, right? When you have some shadow, if you sort of take away the object that is creating the shadow, the original object is still there, right? And that is what is happening here. So it does not mean that the original object is gone, right? It's just shadowed for that particular scope. If you remove the thing that it is shadowing, it comes back in scope. So here is an example. So we say let x equals 5. So x is 5, and then we define y, right? We sort of say we are going to define y and the way we define y is we are saying let x equals 10 in x. This is quite silly. You might even ask, why are you doing this? We can just do 10 directly here. But there is a reason for doing this, right? When I say let x equals 10 here, this x shadows the previous one. Okay. So in this scope, this expression, the body of just this expression, the x is going to refer to the x here, which is shadowing the previous x, right? So the value of x here would be 10 because this inner definition shadows the outer definition. Okay. But now when this expression is complete, right? And but now when I refer to x here, this is a lexically scoped expression, right? This is the whole thing is an expression, right? And this definition, this binding here is only visible within this expression. So when I refer to x here, it is going to refer to the original X. I mean, this is an artificial example. We are not going to sort of um, write real programs like this. Just bear with me, right? So I'm sort of going through this in painful detail just so that I get the point across. So you will find the strange behavior when you write real programs. I'm just going to try to preempt that by giving you some idea. So this whole expression within its body defines an X, right, which shadows the outer definition in this scope, right? This scope where you define refer to X uh, is being referring to this X, but the scope is, this definition is out of scope here in this X, right? It's sort of sitting within the body of this definition here, this expression here. So when you refer to this X, it's going to refer to the closest in its scope. The closest referent in its scope is the original X, right? So Y happens to be 10, right? This will be 10. And this X happens to be the one that is defined in the outer scope, in the closest scope for this expression, which is X equals 5. So the whole expression evaluates to, sorry, the whole expression evaluates to 15, right? So if you can understand what is going on in this particular slide, you'll save a lot of pain, right? So um, is the indentation important? No, the indentation is not important. So I can write it as, so there was a um, question on the chat. If you have questions, I can see the chat window. So just post something. I might not get to everything, but um, if I see it within time, I'll try to answer it. No, the indentation is not important. So it's not like Python. Um, yeah, so you can write very bad syntax like this, right? It's sort of unparsable. Uh, can you please clarify about extra space? What is the extra space? Are you referring to the indentation? Misa Shivaram Prasad. So you had a question. So we just happen to write it like this because it's convenient, right? So I can write y equals, yeah, that's also not important. You can play around with it, right? So this is also not important. And the right hand side of the variable declaration, yeah, so you can do that. Let's say y equals x plus y. Yeah, you can do that, right? So let me add a new expression here just so that x plus y. Yeah, you can do this. Sorry, I need a in. Yeah, so we can do that. Let x equals x plus y is also good question. So you can do this, right? So no, this Krishna Gopal Sharma has a very nice question. So the question is, what happens when I define x equals x plus y? That's a really good question. So this is the question, right? It's a good question. So essentially, this is what yeah, I should have included this example. Thanks for asking this. So here we defined x equals 5, right? And when we are writing x plus 5 here, this x is going to refer to its outer scope, right? The x here is going to refer to this x. This x is not defined yet, right? So the x here is not going to refer to this x. It's just going to refer to the x here. Yeah, so that's going to just fly. Let me, just so that I'll show that I'm not, so I can write x plus 5 in x. So what will be the result of this? It will be 10, right? Because what is happening here? We define x plus 5. This is going to be just an expression, right? And that expression is going to refer to the variables in its scope, and the variable in the it refers to x, and x is previously defined x equals 5, right? So this whole thing becomes 5 plus 5 essentially, right? And we are defining x again, so that x becomes 10, and this x is going to refer to the innermost one, right? So the closest one is this x, which happens to be 10. Right? So really good question. Any other questions? You can quickly type or just shout out. It's, I mean, I like a lot of interaction. I don't mind not covering the material, but I think without interaction, it just seems like I'm talking to a wall, right? So really glad that you're asking questions. Okay. Yeah, so just play around with this, right? So one thing I would strongly recommend is um, I like Jupyter notebooks because I can actually type things out and see what the result would be. So I encourage doing all of this yourself, right? If you have a question, just start writing that, right? So and then finding out answers yourself. So this again, I said we won't complain about syntax, but the syntax might be a bit weird when you start looking at the syntax initially, but you'll get used to it eventually. So all you need to think about is let has a variable binder, right? Some expression here. It could be as complicated as expression is allowed in some other expression here, right? And this pattern is really the pattern, the same pattern here, right? So you can sort of interpret this as this one, where you say let x equals 5 and this whole thing is an expression again. Okay, good questions all around. So I think I'll put it back to what it was. Yeah, okay. So, okay, so that was let expressions. You can also have let at the top level. So what does that mean? So far we've seen let with let binder equals expression 1 in expression 2. You don't need this in all the time, but this form is only allowed at the top level of the program text. So um, so unlike C, right, where every piece of code that you execute needs to be within a function, or even Java, right? OCaml in that sense is like Python, where you can just write pieces of code and it will start executing all of that. You don't need a main function. We won't have a main function. So essentially, the OCaml compiler just goes through the definitions that are defined in the program and then evaluates each one in the order in which they appear, just like Python, right? And the way to define expressions at the top level is you can do let x equals e, right? And that sort of implicitly says, oh, this let binding holds for the entire rest of the program text, right? So if you have a file where you've defined that, it sort of says, I'm going to define x, and this is going to be the value of x in the rest of the program in that particular file. Okay, so why is this useful? Here is an example. Observe that I'm not using in. So that's the first thing that I want to take away. I'm defining two strings here, a equals hello and b equals world. Okay, so of course it says a equals string and hello, b equals string and world. And observe that I am defining another top level let definition where I say c equals a, this symbol caret symbol b. This symbol is what we use for string concatenation in OCaml. Okay, so this is how you take two strings and put them together. So when you do this, we define a new string, which happens to be hello world. So you can of course make it sensible, something like this, right? So These are not, I'm not defining each one as let in. So I've defined A, I've defined B, I've defined C. I can refer to A, B, and C in the rest of the program, right? So these are known as definitions. Yeah, okay. So and let's move on. So definitions are top level let equals x equals e without this in, right? So whenever you do that, you're sort of defining, you're essentially giving a name to a value. So right hand side evaluates to some value, right? We know that expressions, um, the dynamic semantics is you sort of reduce them, and if they reduce to a value, then that value will be bound to x, right? And the definitions just give name to a value. Definitions are not expressions or vice versa, right? Definitions are a different class of things. So you have expressions, we saw values, definitions sort of sit outside here, but the definitions syntactically contain expressions, right? So this thing is an expression here. This whole thing is a definition. E is an expression. Okay, so that's definitions for you. We can also try to give precise definition of the semantics of the let expression, right? We'll just do that here. So the syntax for let is what we saw earlier, right? We said let x equals e1 and e2. We have to give, when we define semantics, we have to define both static semantics and dynamic semantics. What does the compiler see and expect, and what is the result of running that expression, right? So the static semantics is this, right? So um, the way to read this is if e1 has some type t1, let's say e1 has some type t1, we are going to evaluate e1 to get a value of type t1, and we are saying x is now referring to that value, right? So it must be the case that x is also of type the same type, right? Assume that if e1 is of type t1 and x is of type t1, if e2 is of type t2, right, with the assumption that x is t1 in that body, then this whole expression, right, let x equals e1 and e2, this whole expression has type t2, right? So that's the static semantics. And we are sort of omitting some detail, but that's not important. So if you sort of get the high level idea of what is happening here, then you'll be fine. Then the dynamic semantics is going to say precisely what we had seen in the examples, right? Take e1 first and then evaluate it. You will evaluate it to some value, right? Let's call it v1. And in e2, wherever you find the variable reference to x, substitute the value v1 for it, right? If I say e2 is just x plus 1 and v1 happens to be 0, then that becomes 0 plus 1, right? And then evaluate the substituted expression to some v2, right? And that's the result of this whole let expression, right? So if you take this let expression, if e1 evaluates to v1 and substituting v1 for x in e2 evaluates to v2, then this whole expression evaluates to v2. Okay, so this is again, I'm sort of glossing over some detail which will make it concrete later, but this is just to give you a feeling for how we will tend to define the semantics of expressions in a formal way, in a very precise way, right? So once this is not yet fully formal, but once we formalize this, by which we completely write the meaning of this let expression, the compiler will follow it, right? If you understand that one rule, you can know how the let expression works in every instance, right? There is no deviation, there is no corner case. But here I'm not doing that. It's still not there yet, but we'll refine it later. Okay, so yeah, this is an exercise for you. You can play around with it and find it out. So in OCaml, we cannot use plus for floating point addition, right? If I use plus, it complains, right? But if I use plus dot, which is very strange, right? If I use plus dot, it works. It says gives you the right answer. Just using plus doesn't work. So I want you to find out why using plus. If you do this, you will get an error, right? I'll just leave it at that. I'm not going to run that code. I just want you to run that code and see what happens, right? If you just run plus, it will complain, and instead we have to use plus dot, and that works. Just find out why that is the case, right? You can just play around with it. The answer is going to be very simple, but play around with it and find it out. And once you find it out, I want you to write down the static semantics for plus and plus dot. Just the by static semantics, I mean something like this, right? So um, yeah, you'll sort of see what I mean. Uh, Again, these exercises I'm not going to evaluate. You don't have to send it to me. This is just for your understanding, right? But if I tell you there is some exercise, just try to think about it, right, after the class, um, because I think these are like leading questions, and these are the sort of questions I might ask in the final exam, right? So let's just put it that way. Sir, do let expressions always return values? Yes, they always return value, right? So there is a question on the chat. I'm looking at the chat. So yeah, this whole thing is just evaluating to 15, right? There is no return. Um, yeah, so there is no notion of return um, in expressions, but you can sort of think about the whole expression. I'm reading in the chat. Evaluates to a value, and in this case, this particular example, which is let x equals 5 and let x equals 10 and x plus y, um, evaluates to 15. Oh, okay, this is a good question. So does y equals 10 and x plus y return something like x plus 10? No. So here is um, okay, here is an example. So the question is let y equals 10 in x plus y return something like x plus 10. Let me change the variable name just because my scopes will not, I might have an X in scope. So what is going to happen here, right? So when you look at certain expressions and you refer to variables, those variables have to be in scope, right? If the variables are not in scope, then the compiler cannot tell you anything about what that expression will be. So you just get this unbound value x1. Okay, so that's the answer. Good question. The reason is that you can sort of look at a deeper reason for this, right? The deeper reason is that I don't know what x1 is. I can't give you the static semantics of this, right? X1 could be an integer, and x1 could be a banana. I can't add banana plus an integer. So the compiler just says, I don't know what I can do with this, so I'll just say the value is unbound. Okay, good question. Okay, so that is what I had for expressions. I'll delete this thing. Okay. So let's start the next lecture. And I think in the remaining few minutes, I'll just maybe give a brief introduction of what I'm going to deal with. So the next thing we are going to see is functions. Okay, so the thing we said we are doing is functional programming. So obviously there has to be some functions in it. So here is functions for you. The way I deal with functions will be sort of from ground up, right? So again, we are studying paradigms here. We are not just looking at how to program. So it will take a strange way of dealing with functions, but this is sort of taking some abstractions and then taking it apart, right? Taking it down to their essence and looking at what they actually mean. So we'll sort of go through that step by step. So previously we saw syntax, semantics, a bunch of expressions, if and let, and definitions. Today we will look at functions. So OCaml has support for anonymous functions, anonymous function expressions, right? For people who have sort of programmed in Python and say the recent Java versions, anonymous functions, the hot term today is lambdas, right? So when you say lambda, you're sort of defining a function, but you're not giving it a name. You're just defining a function without giving it a name. So what does that mean? Without giving it a name, you can sort of uh, define the arguments to the function and the body of the function, right? But you don't name it. And this this predates all of this fascination, newfound fascination with lambdas in recent languages, right? Um, all of the modern languages have lambdas. So Python has lambdas, JavaScript has lambdas, Java 8 has lambdas, C++ has lambdas, right? So these are sort of becoming an essential toolkit in all of these languages. And lambdas sort of form the basis of functional programming languages, right? So we don't call it lambdas because lambdas is just a term. We just call them by what they are. They are just anonymous functions. Anonymous because we don't give it a name. So the syntax is this, right? So you sort of write fun binders, several binders. So you can have x1, x2, x3, x4, x5 to xn, right? They could also be other binder names. And then we have this minus um, greater than, so which is you interpret that as an arrow, and then some expression, right? And that is the syntax. And when you define an anonymous function is just a value. There is no further computation to do. You don't start evaluating anonymous function because you don't have the arguments to evaluate it, right? In particular, we can't evaluate E until all of these arguments are applied. This is just like what you would have in C, right? So you define a function that's just a thing. In order to start evaluating the body of the function, you need to supply the arguments. And similarly, that's a fact here, except that unlike C, where you don't, the typical C functions are definitions, right? But anonymous function here is just a value. So it's just a value with no further computation. So wherever you can write values, you can write anonymous functions. So by extending the definition, values are expressions. So wherever you find expressions, you can write anonymous functions. Okay, so here is an example. So here is an anonymous function that takes one argument x and then in the body does x plus 1, right? So and all it's doing is takes a value and then adds 1 to it, right? And the static semantics, the type of this function is being told as int arrow int, right? What does that mean? This arrow in the type signifies it's a function type. Okay, and the function type takes one argument integer and then returns one result, which is also an integer, right? So obviously this expects one argument, which is an integer. You can give it any integer, and then it returns x plus 1, and that expression is also going to have type integer, right? So that's what we define here. And yeah, so this is what I just mentioned. The function type is int arrow int, takes one integer. Yeah, so someone is actually seeing ahead. So there is a comment from Shartak Kapoor who says if you change it, yeah, so you have to. So the question was, if I just changed plus to plus dot, will the type be float? It's a really good question. It won't be because it will be a type error. Because what is happening here is this 1 is an integer, right? That has to be a floating point number. Plus dot is a function that takes a floating point and then adds it with another floating point. 1 is not a floating point number, it's an integer, right? So that's why the error message says this expression has type integer, right? This expression 1, but an expression was type expected of type float. Did you mean 1 dot, right? OCaml has this weird notation, right? You can write 1.0, but you can also write 1 dot. It will be the same thing. So yes and no. Yes, the comment. Yes, the comment is that if you change it to plus dot, the type will be expected to be floating point number, and no, you have to change the 1 as well. So that it becomes float or a float. This is type inference at work, right? So it's sort of we haven't specified what the type of this function should be. Just by changing the body, we are expecting a different type, and the same for doing this, right? So I'm using string concatenation here and a string. So OCaml is automatically saying this is a string or a string function. So this becomes quite handy. You don't have to, you don't have to specify the type. I'll stop here. I think I'm already out of time. Really good questions. I would like the class to be like this, right? So please do ask questions. Otherwise, you won't challenge me. Put me in a spot, right? So only then I will sort of give my best. If you just don't, I'll just like read the slides and walk away. So ask questions, really good questions today. Okay, so I'll talk to you on Friday. On Friday, what we'll do is I'll sort of run through my Docker setup and basic Git commands, right? So that you can play around with the Jupyter notebooks. I will also, I have uploaded for those who have Windows Home or Windows Student, right? Docker for Windows does not work on Windows Student. It does work on Windows Home. But anyway, I've made a Ubuntu VirtualBox image, which has all the setup already done. If you if you can't install Docker, then I recommend doing that. It has Docker installed and ready to go. So it's already on the course webpage. So if you go down to resources, yeah, so you'll see that. I'll just point to where that is. So if you go to resources, you go all the way down. Yeah, there is a VirtualBox disk image with some instructions as well. So you can sort of it lets you get started. We'll cover some of this. I mean, it's quite large, but anyway, you can slowly download it and play around with it. We'll cover some of this in the next class. And yeah, so try to have questions ready, right? So give this Docker installation and getting the notebook set up tomorrow, and come with questions on Friday, and then we'll see those questions. Okay, thanks very much. Talk to you on Friday.